Today we will explore nMOS transistor characterization using Cadence. I will cover essential analysis like IV characteristics, power dissipation, output impedance, and the early voltage. I will also discuss how to extract key parameters like threshold voltage and channel length modulations parameters. Whether you are new to Cadence or looking to refine your skills, this video will guide you through the essentials of nMOS characterization. So let's get started. So to start the designing of the nMOS transistors and analyzing, we need to first create a cell view inside of a library. So if you can just follow my previous playlist, that is Cadence Virtuoso overview, you will easily understand what does it mean, why we need to create a library, why we need to create a cell view, how can we operate these Cadence tools efficiently. All the basic things I have already discussed here. So for now, our motto is to analyze a nMOS transistor. So we will create a library first. After clicking on file, I will create a new library first for that. So for example, I am putting here the name TRN. Okay, so the library name, you can put any name here. It could be your name also. That doesn't matter. So the technology file, I will click on the attach to an existing technology library because I will work with SCL PDK. So that library already exists in my Cadence Virtuoso environment. So that's why if I click on apply, so from this window, I'll select my SCL technology library from here. That is TS018_SCL_PRIM. So then I will click on OK. You can cut this window now. So here you can see the design library TRN successfully attached to technology library TS018_SCL_PRM means I have successfully created this library. So inside of this library, I need to create the cell view. So I will repeat the same step again, but this time I will create the cell view instead of the library. So I will select from this library where is that TRN library that I have created. This is my TRN library, and I will write here nMOS as a cell. So if I click OK, so you can see schematic window came. So inside of this schematic window, I will design my circuit. So from this schematic window, I have to take instances. So this is the instance icon. I can click here easily to take instances. Otherwise, I can click I button from my keyboard. So here you can see the library name came. So from here I will select obviously the SCL library because I will select all the transistors from the SCL. Which cell I will take? The nMOS_18. I will choose from here. I'm once again saying, if you need to understand what is this means, that _18, why I'm taking _18, why I'm not taking the _33, just follow my previous playlist, that Cadence Virtuoso overview. You will understand everything easily. Okay, so for now I will not change anything from here for now. So if I just click on the hide and if I place the transistor here, you can see the transistor placed here. So I have already taken the transistor here. So I have to connect some voltage sources with the transistor. So for that, I will go and select the analog library from here. Okay. So inside from the analog library, I can choose the VDC, that is the voltage source. Okay. So I'm putting here the value 1.8. So if I click on hide, so I will put that here. That will be my VDS, and another one I will put here. That will be my VGS. Okay, that's it. So now I need to take ground. The ground is GND. From the analog leaf you can take the ground. So if you write GND inside of this cell, you can see the GND symbol came, taking the ground for the VGS and the VDS as well. So that's it. Now I have to connect the wires. So if you press the W, then you can take the wire directly. Just click on the point to point. Okay. So connect the wires. I need to connect the body also of the transistor. So I'll connect directly to the ground. So that's it. Now I need to save the circuit here. If you have to click the check and save. If you are clicking on the check and save, then you can see if there is any warning. You can see from here if you click on the check and save. So see, this is my net 1, net 2, and this is my ground. Okay, so you can see here all the parameters are mentioned also here or here also. So this is my schematic, and from this schematic I will run the ADE. What is the ADE? It is nothing but the analog design environment. From that ADE, we will analyze this transistor. I'm clicking on ADE L. So the ADE window came. After the initialization, completion of the initialization, we will set up our ADE. First, I have to select my model libraries. Here, I will select my model libraries. From here, I have installed inside of the Cadence. Let me take that a little quick. Yeah, now section I will select the TT_18. So why I'm taking TT_18? Because TT stands for type, and you can see there are many sections are there. So what does it mean? You can know. I'm saying again, you just follow my previous playlist. Okay, the Cadence Virtuoso overview. You will understand everything. So I will just click on apply and OK. My model library setup is completed. Now I will go for the analysis. Choose analysis. So here I will take DC analysis first. So save DC operating point. I need to save the operating point, and component parameter I will select. So see one thing here. I have taken here, this is the VGS and this is my VDS. So both are 1.8 and 1.8. Okay. So first of all, I will select the VGS, okay, as my component parameter. So if I select my VGS, I will select my DC voltage from here. So the DC voltage has been selected. Now I will go to the choosing analysis window again. So here I will start from 0 to 1.8, okay, and I will put the sweep type automatic for now. Apply. So from this ADE, I will now set up my output. So here I will click to be plotted and select on design. From the design, I will select this wire and the node. This node, the drain node. Okay. So if I'm going here, you can see the M0D has been selected and net 1 also selected as an input. So if I run the simulation, you can notice, you can notice here. So this is my input that is going from 0 to 1.8 here. So I can hide the input for now here. So you can see this is my, what is this? So you can see this is my VGS ID versus VGS curve. Okay. So this is the way, this is one way you can do the things. Now if you need to do the parametric analysis, okay, so the another way I want to show you. So for that thing, just let me delete all these things that I already set it up. Now I will not give any value here. Just I will write the VGS as the DC voltage, and I will also write the VDS here. Okay. Now what will I do? I will save the circuit. Remember one thing, you need to save the circuit every time. Whenever you will see one start sign is there, means you need to save your circuit. Okay, the circuit has been saved. Now you need to go again to the ADE. Now if you click on the design variable and copy from cell view, you will see the VDS and VGS came. Okay, so here I am taking 1.8, the value, the initial value I am giving here. The thing, now I will choose my analysis from here DC and save DC operating point, but this time I will choose the design variable. No, I will not choose the component parameter this time. Okay, So design variable from here, select design variable from here. So I will select the variable I want to sweep. So first of all, I want to sweep the VDS. Now start stop 0, stop will be 1.8. Okay, my VGS is constant. I am just sweeping my VDS. Okay, after taking my outputs, see what is the result? See this curve. This is the ID versus VDS curve because I sweep the VDS from here. Okay, so if I want to do the parametric analysis thing, okay, so for that thing already I have selected, I have taken the parameter here, the design variable here. So now if I want to do the parametric analysis, so I will go for the tools and I will click on the parametric analysis. So here I have chosen, in the analysis window, I have chosen the design variable as VDS. Okay, so I have swept the VDS from 0 to 1.8. So I will select here in the design variable the VGS, and that will be from 0 to 1.8, and I will keep that step mode as auto. So now if I sweep the thing, what will be my result? Yeah, see here, this is my parametric analysis. So if I just click on plus, so here you can notice for 0, for the VGS 0, you are getting 0 here, the red. Okay, and the highest one is 1.8, the VGS is 1.8. I'm just sweeping my VGS. Okay, this is the different VDS value, 0, 0.12. You can notice here it is already written here, and this is my ID. So what I am just saying, I'm just trying to see the ID versus VDS plot at different VGS value. Okay, so at 450 millivolt, my ID versus VDS will look like this. 900 will look like this. 1.35, 1.8 volt. This is the parametric analysis of ID versus VDS plot. Okay, so if I want to plot my ID versus VGS, so how I will do that? So the exactly same thing I will do, but I have to do the opposite thing. Means here in the DC analysis, I need to edit the design variable as VGS. So everything will be same, just the design variable will be changes. Okay, so then apply, okay, and from this parametric analysis I will select the VDS from here and I will run again. See here, the VGS curve are there. So you can see the same for different VDS value, my ID versus VGS plot has been plotted. Okay, this is my parametric analysis of ID versus VGS. So you have seen the ID versus VDS, ID versus VGS. Now if I want to calculate the DC power dissipation of this transistor, how can I do that? That is the very interesting thing. So for that you need to save your output here. From here I will save the output. Okay, so after saving all the outputs from here, I will click on apply, okay, then I will run again the circuit. Okay, so now if you go to the result, then direct plot and main form, you will see here plotting mode append, analysis DC. Which function I need to see? I need to see the power, the total power. Okay, I'm just clicking here to add add to the outputs, and if you just click on plot, you see the total power dissipation came. What is my total power dissipation at 1.8 volt? It is 438 microwatt. You can see here. It is 438 microwatt. Okay. That is how we can also calculate the power dissipation.